Welcome everybody to the next installment of the Python Live Series webinar. Myself, I am Amber Such. I'm a specialist recruiter here at Amicus Recruitment, where we cover recruitment for Python, JavaScript and Golang. I'm here today with the fantastic Rahul Agrawal, who is the machine learning engineering leader at Meta. And he's going to be talking us through graph neural networks and how they can provide a natural formalism for modeling real life problems. How are you today, Rahul? You hear me? Rahul?
Yeah, hi.
I just said, are you all right? No worries. You're into it already.
Yeah, hi. So sorry, I was just answering the question. So I think, yeah, thank you so much, Amber, for introducing me. And yeah, it's a great pleasure to have this opportunity to speak to all of you. Am I audible?
You are, yes. So I can hear you completely fine. I will just say to everyone as well, as we go, there is, obviously you've seen the little Q&A box. So please feel free to ask any questions. We'll stop and ask a few, but we will also have time for a Q&A session at the end. So we'll kind of go back through and answer any questions. But yeah, I can hear you. I can hear you fine, Rahul.
Perfect, cool. So today, what I'm planning to do is to talk about graph neural networks, and this is a very brief introduction to a very rich topic about this. And so what we want to do here is that this is a brief overview today. As one of our friends asked, are these graphs as in 4-color theorem? Yes, these are the similar kind of graphs. It's just that we are sort of building up a mechanism of how to use neural networks on such kind of graph. So primarily what we are going to do is to have a very quick refresher of graph basics, and then we jump into what is called as graph representation learning, like how do you represent graphs in a manner that is useful for machine learning. We take a very quick look at what are graph neural networks, and then we go to a bunch of problems like node classification, link prediction. At the end of the thing, we will see that once we have a good mechanism of how to address graph learning, how different applications can actually pose as graph. So a very non-conventional applications in terms of images, text, and so on, where graphs can naturally arise. So let's just start our thing with a very simple basic graph concepts, right? So what is a graph? So a graph is typically, like mathematically we talk about, we usually call represented by a G. G is like a graph which consists of vertices and edges. So let's take a Facebook graph. So the users are vertices, and connection between them, friendship graph between them, or they are friends of each other, that's the edges. You can take Twitter graph where users are again vertices, and when you follow somebody, that's an edge. So if you take an edge, talk about E, it has two endpoints, U and V, which are all both what you call as vertice, and U is called the neighbor of V and vice versa. And these two vertices are called adjacent. These are just terminology that is typically used. Now, each of this edge can be directed or undirected. So in case of Facebook, it's a undirected graph because if you are a friend of A, then A is also a friend of yours. In Twitter, this is sort of an directed graph. So you may be following, say, Obama, but Obama will not follow you. So that's a kind of directed or undirected concepts here. Now, a graph is called a directed graph. Like, for example, Twitter is a directed graph because all the edges are directed. Like everything or all the connections that we're talking has a direction associated with them. And the graphs can be called as undirected if the edges are undirected. So like say Facebook graph, we can also talk about graphs like basically co-author graph, where two people have written a research paper together, or maybe you can talk about GitHub graph, where a project and people, so two collaborators can be linked together if they have a common project, where they're collaborating. Or you can have project and user graph, where user is linked to a project when they are a committer on that project. Now, there's another information that we typically use, which is associated with every vertex, that is called as a degree of the vertex V, and which is the number of edges that are connected with V. So these are the very basic graph concepts that we want to start with, and this is what we're going to use throughout the topic, throughout the talk. Now, let's just take a step back. And what we want to understand, before we jump into processing of the graphs, we want to have a good understanding of what exactly is representation learning. Now, as we all understand it, so representation is kind of a formalism or a modeling or abstraction of a real world situation. So what are good representations? So let's assume I want to build an AI system to maybe say measure IQ of a person. And if I take a representation, which is where I take the person and represent by the color of shirt they are wearing. Now, obviously this representation is bad because based on the color of shirt, you cannot predict IQ. So what it means is that if you want to have a good AI system or a good machine learning system, it is super critical that we arrive at representation of the objects which are actually good or informative of the actual planned outcome. If the same for the same person, I would want to predict, like, say, dressing sense. Maybe the color of the shirt would have made a lot of sense because the same. So as you understand, right, the same representation can be good for one task and may not be good for another task. Now, conventionally, in machine learning, in the prior, like before we had deep learning and so on, what used to happen was that, like, we have a lot of representation was done through hand. So there will be usually what will happen, there will be like some PhD students whose doctoral thesis is about figuring out some new features or new feature engineering, and specifically this used to happen a lot in natural language processing. The whole PhDs used to be given based on like feature engineering. How do you represent a text better, or how do you represent image better? And that's used to happen. This particular approach of doing feature engineering by hand has a lot of challenges. So number one is that it's biased, and we have seen that now. Once we have started seeing the proliferation of AI into a lot of segments, we have started seeing that AI is actually biased, like it's actually giving biased results. And that's happening because when humans were encoding the representation, they sort of tend to introduce their own biases. It's their bias about what is important to represent. And a very simple example, let's assume the same IQ prediction system. So I, as a person, may have a bias that the CGPAs or the GPAs are the most important thing. So I might just say that let's look at all your exams from like standard 1 to standard 11 or 12, and I will encode that as an important feature. And I might completely ignore your other capabilities. And that's a bias that I have introduced into the model. Sometimes I may not be even aware of a lot of facts, like for example, like IQ may have some manifestations in terms of how good you are with, like, say, language. And maybe I am an engineer and I never thought that language is an important component of IQ. So I just ignored that. So that's an incomplete problem. So these were the key aspects that were there. And obviously it was very expensive and time consuming. Like, it's basically manually trying to like figure out, like, reverse engineer what could be a good representation of this thing. So what happened is that when AI or machine learning started moving into the direction of deep learning, where we started getting a lot of neural networks, what we started saying that researchers asked this question that, okay, so why do we need to do the feature engineering? Is this the right thing to do, or can't we have data learn about themselves? And there's a very famous quote by Geoffrey Hinton when like in 2006 or prior to that, when they were talking about, like, how do kids learn? Like when human kids learn about a lot of concepts, like that 3-year-old or a 2-year-old, we don't teach them everything. We don't take them out and we don't show them that this is a tree, this is a dog, or something like that. They just observe it. And sometimes, like once or twice in a day, we tell them that, okay, this is a dog, or by the way, this is a cat, and human minds just learn about it. So that was a motivation that why not generate representations automatically? Like, why do we need to have a human generated thing? And the key idea was that, like, you take up the data and then generate a lot of nonlinear transformation. Nonlinear transformations means like, just let's assume I take a representation of humans, and I have like all the GPAs which are associated with them, their language, like if they have done something, like all the exams they have written, like whatever data I can get about them, and then start making combinations. I can say that maybe the score of first standard cross score of 10th standard, or score of like like some SAT exam cross something, like all sorts of combinations. So what effectively we are trying to do, we're saying that I am just taking all the available data and creating all combinations out of it, and that could be one learning. And then basically pose the learning problem in such a manner that a representation is good if it's able to explain my task. So whatever representation I'm using, and I build a system on top of it, if I'm able to predict the IQ well, then that representation is good. So that's the basic idea of representation learning. And the whole idea was, the next step which for this whole idea was to have not only task specific learnings, but rather task independent representation learning. So that's the key idea for representation learning. Now, how does that apply to our scenarios? So we extend this back to, say, talking about graphs. So like the natural extension would have been like, how do you represent a graph? So I know that graph is appearing at a lot of places. It's a very informative mechanism to represent our real world. But then how do you represent a graph into machine? And luckily what has happened is that traditionally there is a lot of algorithms that we have done. Like if you think about computer science, there is like basically, if you go to booking.com or if you go to our city mapper. So city mapper, if you feed in that I want to go from, say, Canary Wharf to, say, Tower Bridge, it will connect up the edges. It will say that pick up a bus and then pick up a train and so on. So it's actually a graph traversal algorithm. And so traditionally we were always using a graph as it is. We are just saying that let's just take the vertices and edges and keep a adjacency list, which is like what are the vertices which are adjacent to a given vertex, and then compute them. Like we have a lot of algorithms around shortest path, about traversals, about DFS, BFS, and so on. The challenge which was there that like when we start talking of graphs at the scale of, say, Facebook or web graph, like we are talking of huge computational complexity. So just to give a sense of it, right? So when we talk of web graph, which is all the websites and the connections between them, we are talking of like a graph which is of like easily up to the order of like 100 billions or 500 billion kind of nodes, and like rich connection between them. So on an average, even if there are like, say, 20 or 10 to 50 links out of a page, we are talking of something like 5 trillion edges and a 500 billion node graph. Now this is extremely complex. Like we cannot apply a standard traversal algorithm because of the computational complexity. So a single BFS or DFS is like orders of n or n square kind of thing. So there is a huge computational complexity. There is low parallelizability because most of these algorithms are inherently non-parallel. So you cannot, like, you can actually parallelize them, you can do you can actually split them, but it's not very easy to parallelize. You have to do rich constructs around message passing and so on to make sure that it's parallelizable. And finally, the whole machine learning was difficult. Like I can do traversal algorithms, but when I want to do machine learning, so the first question that a machine learning algorithm asks is that where are my numbers? And I'm talking of like edges. It's a categorical. It's like a node and a vertex. There's no numbers there. So machine learning cannot directly apply to a graph system because like we are talking of nodes and relationship, and they are talking of like basically numbers. So like let's assume I take up a Facebook graph. I say I am related to, say, Amber. Amber is my friend. But then machine learning will say, okay, tell me the degree of friendship. Like give me a number between 0 and 1. So there's a challenge which was there. And so, yeah, any question at this point?
I think we're all good to continue on. If anyone does have any questions, as they pop them in the Q&A box, and we'll answer them as we go.
Makes sense. Cool. So yeah, so then the traditional graph representation, like basically to address the ML algorithms, what people did was they came up with a lot of connectivity algorithms. So they say that let me start representing a graph where what I could do is that I can take a vector of like, say, d dimension, and then I basically represent it by either the neighbors or like how I can do a random walk. What I can do is that I can start with each node of the graph and randomly walk the graph and then keep on doing that. Like that's a random walk. Like pick up a node. I can say like I can start from my profile on Facebook and then I pick up one random friend. And
we have had a question. So David's asked, could the degree of friendship be worked out from how often you interact?
Yeah, it's a very good question, and we could actually we can like basically deduct that based on because like the more you interact with someone, that gives you the more what you call as confidence in that particular edge. So, for example, if I am a person who is just randomly doing like a mass messaging, and so although a lot of people may appear friend to me because I just accumulated a huge network, but then the strength will be obviously like if there's like some person whom I'm talking 10 times, it's obviously more. So that's a very good point. Like the strength usually plays a very important role but based on the number of interactions that you do. It just like basically reinforces the confidence that this edge is a true friendship edge rather than just a communication edge. And a very good example could be Twitter as well. Like there are people like, for example, say Boris Johnson, who is a PM of UK. Now he has a lot of followers, and whenever he posts a tweet, people will be reading them. But a good friendship would be one where somebody sends a message to Boris Johnson and he replies back. So I think that's the interaction which clearly establishes that it's not just a messaging, but it's also a interaction which is more powerful. So yeah, it's a very good point. So what I like coming back to the random walk. So what I was trying to say is that like one way to represent graphs is to pick up a node and you jump to a random friend, and then from that friend node you take another random thing. So if, it's easy to understand that once we start traversing this graph, depending upon how closely or how tightly this graph is connected to each other, we can land up in different nodes. So this is what a random walk does. So we can actually take a graph and then say perform a random walk, and then they say that after say infinite, like after say 10,000 times taking this random jumps, where do I land up? Which node I do land up? And that could be a representation. Or I can keep on doing the random walk and then say that the top 1,000 nodes where I typically end up, that could be a representation. So these are all various ways of representing graph. Key point to note here is that like these representations are complex because understand graph is like if you talk about text, it's a linear structure. You can say that there is word followed by word and so on, like a sequence of word. Graph is not like that. Graph is a multi-dimensional structure, and that's where the complexity of representation comes to, and that's where the modern approaches come. And these what they say is that like we want to represent graph by two things. One is either the graph structures, like inherent structure of the graph, or the properties associated with graph. And usually there are some mechanisms which are built. Yeah, pardon. Is there any question?
There is. We've got two questions. So the first question is from Mustafa, and he said how to shape training data from different resources into a graph representation, i.e. if you have Facebook users with different activities such as sport and work.
A very good question. Okay, so I think I'm so happy that Mustafa asked this question. Thank you so much. Right. So yeah, I think just to make sure that like people understand this, like what's a challenge here is that like if you have different kind of activities, we are inherently talking about different kind of interactions. So it's sort of like there is a friendship graph, and on top of it, I'm actually putting a lot of different other graphs. So people can be related through work, like they work on the same place, or people may be related through sports, which are like similar interests, or they may be following similar people. So I think there's a lot of such information, and in our theory, we typically call them as heterogeneous graphs. Now, heterogeneous graphs, there are multiple ways of doing it. In case we want to, we can actually merge all of them together in the sense that we can just say that the random walks when we are doing on top of them, like we actually can do it on a composite graph, which is incorporating all the edges. But the challenge there is that like a work relationship may be a very serious relationship. It is like very confident, like you're working together. It means like you have to have high degree of communication, whereas a sport activity may not have it. So usually there are other kind of tricks that are done. Some of the tricks what people do in neural network is to like pick up one of the graph and then feed it into the network and then pick other ones, as we see later. The other point could be like have separate what you call a representation for them. So In terms of how is the input fed into the network, very good question. So usually this question we are going to see a bit later. Like I'm going to cover that in our talk. So I think I will park this question for a future slide, because this is exactly what I'm planning to answer. Cool. So moving on to things, right? So before we jump on to actually figuring out how do you do graph neural networks, I just want to give a very simple yes, answer is yes. For a very millions of nodes, we indeed use sparse coding, because a dense coding is like usually, like for example, we call it as one hot encoding kind of setup, where we can use, or we can also do is to take a graph and say multiply it by another matrix, or like a random precision to generate a sparser coding. Yeah, we do use that. And this is in fact the only way to do this to represent the a graph with million edges. Cool. So now when we talk about neural networks, yeah, by the way, feel free to keep on asking questions. I'm like perfectly fine. I love this kind of interaction. So don't worry about what we are discussing. I will try to fit in wherever we can fit the questions. So just feel free to keep on asking the questions. Yeah. So we till now understood like what's the graphs are all about and what does graph representation means. And so then one of the technique that I'm going to discuss today of processing the graphs is very is based around neural networks. And I just want to give a very two-liner introduction to neural networks. So neural networks are nothing. They are like a basic computation unit. And the idea here is that on the left-hand side, if you see in the thing, basically what we're saying is that x1, x2, xn are sort of like input features, or like what these are input associated or representation associated with a node or an edge or something like that. And so what does neural network does is that it calculates a linear combination, a weighted linear combination. So what it does, it takes the value of x1 multiplied by w1, sums up plus x2 multiplied by w2, and so on. So it's a summation over a weighted summation over all the inputs, and then an activation function. So activation function, like there are two examples I put here, is sigmoid and tanh. But the whole idea here is that the weighted representation is basically sort of saying that I have like all the x's or input features are the if you can think of them as like evidences. So I'm combining the evidences and then doing a non-linearity. Now the reason for doing this activation function is very simple, is that if you do not do them, and if you try to create multi-layer neural networks, we can show through mathematics that it's equivalent to one layer. So if you have 10 layers of neural network and no non-linear activation function in between, which is the function z, then it's equivalent to saying just one layer. And there was a very famous result by MIT professor, I think Marvin Minsky, which said that a single neural network cannot explain most of the functions. So hence we need to have this is a celebrated practice and the backpropagation algorithm, which was proposed by Rosenblatt. And so that's the whole idea, that you need to have a non-linearity to basically enable learning complex functions. So that's the basic idea. So we have neural network, you can have one layer, which a layer have inputs, and these inputs are weighted together, and then a linear combination, and then a non-linearity applied, and then we move forward. So you can put any such multiple layers to calculate more and more complex functions. So now once charged up with this, let's just move on to the major part of this talk, which is around GNN foundations. So what are we saying here is that GNN is primarily graph neural network, and we want to jump into some foundations of it. So let's start with a simple example of node classification. So let's assume you have a graph, say social network, and we want to identify, it can be Twitter graph, and we can say that I want to identify a certain user. Does it has a political bias? Maybe they are centrist, leftist, rightist, or something like that. Or are these people influencers? So for example, my Twitter has no activity, so I'm not an influencer, but you can look at my node and say whether Rahul is an influencer. Okay, there's a question.
There is, yes. David's asked, could the graph be reduced to a smaller graph by finding a number of centroids using something like Hakimi?
Yes, we can do that. We can actually reduce the graph, and it also depends upon the kind of problem that you're solving. Sometimes the problem is like if it's isolated, like it's a local problem. Let's assume you want to figure out like you want to do some reasoning in the graph, which is sort of restricted to your neighbors or like one step neighbor, like basically all the nodes which are reachable by say path of length 2. Then such kind of things can actually work out very well, because it's a local kind of thing. However, if you want to predict a more global kind of, for example, molecule prediction, like molecules can be represented as graphs, and you want to predict them, like what this molecule represent is what protein or what amino acid. Sometimes these kind of methods may not work because you may lose what you call as the overall structure, but you can still approximate them by having a smaller. So yeah, these kind of methods can indeed be used for graph problems. And just to add to it, like as we see in the later of the talk, most of the algorithm that we are suggesting are also sort of an approximation on the local setup. So it's sort of doing like a kind of a construction which is still trying to preserve a local structure. We are not doing it explicitly by pulling out the graph, but it's invariably happening. And what we're trying to do is that let the model learn what's the right local structure that you want to focus on. Cool. So again, another node classification example could be like World Wide Web. So we can actually associate different semantic categories to the page. So that could be a problem. So basically, the problem of node classification could be suggested as you are given a graph which is vertices and edges. You have an adjacency matrix which is called as A, which is like if you have n there are n vertices, then you're saying it's an n cross n kind of a matrix which says that which node is connected to which other node. And then you have sometimes you have node attributes. For example, like if it's a Twitter graph, you can have some a bio associated with a node, so you can have those kind of things, how many times it posts in a day. There are a lot of such features that you can associate. And what you want to do, you want to learn a node representation. So you just want to say that I want to like represent each node by a f, like capital F number of real numbers, which could help me ask various questions about the node. Now, how do you solve this problem? A very simple problem is that, like for learning this matrix H, which is your what you call as your representation, you can actually set it to a random number, and it's a valid solution. However, it's a viable solution, but not a good solution, because that representation is not going to yield us anything. Like every node will have F random numbers associated, and it's not going to help me answer anything. So that's where we came up with a more we can come up with a more recursive solution. So the generic idea of any graph neural network is simple, right? You start with any initial solution. Initial solution could be random numbers of which we call as H. And every time we have H, now what we do, as we said, right, graph is understood by a local properties which are, so that's what we call as like aggregate step, which is like you take the representation and aggregate the structure around your neighbor. So in reality, what it means is that you take all the current what you call representation. So it seems very weird that why it works. So we are saying that you start with the random, each node has a random numbers. Now I say for a node, I pick up all the neighbors and take their representation because they were neighbors, and then regenerate the representation for a node, and do this everywhere. So what's happening is that we are sort of bringing up together that each node should start behaving similar to their neighbors, and we keep on doing this recursively. Now, obviously, what will happen is like if we do it recursively, there will be local structures that will start coming out of it. Now, one thing to note that, right, if a graph is like completely connected, that means everybody is a neighbor of everybody. Obviously, we will converge to a stage where all the nodes will start looking similar. But that's the whole idea. That's the whole idea of most of the graph neural network. The idea is very, very simple, that you start your initialization, which is called as H0, with some random, and you can start with X. X, as we said, like was your node representation or your node adjacency, whatever you want. You just start with some number, and then you aggregate. And if you look at it, aggregate function here, which is basically your sorry. Yeah. So if you look at it, what we are saying is that the aggregation at the kth iteration for a vertex V, it depends upon all the U's, the representation of all the U's. So HK minus 1 sub U is not a complex thing. It's just saying that all the representation of the neighbors at the previous iteration. So you just collect up together all the previous what you call representation for each node. That's your aggregation, and use your previous representation along with the accumulated information to generate a newer one, which is your HK. So it's basically building up your representation from your neighbor's representation. So you are similar to your neighbors are similar to you, and this recursively ideally reaches to a stage where we have a convergence, or we have a stable state where representations are looking similar to the local structure. It's like capturing the local structure. Now, does this converges? Yes. So there are like, depending upon the algorithm, there are mathematical proofs that why does this converge. But just like currently, I just request you to assume that yeah, it happens. But these are the convergence that you can achieve there. Yeah. So sorry, I think there's a slide repeat. Yeah. So basically, this is what we are trying to do. So like we say that we want to like what we just to recap. So what we're trying to do here is that node classification. We want to we started with a random graph. We somehow aggregate the information from the neighbors, and then we regenerated the representation for the current node. This is the basic thought process, right? And then I just want to give you a couple of proposals that people have done in the literature. So one other thing, like this is again related to some place where some question was asked, like how is the input, the graph structure fed to the network? So I think this was Al Hussein's question. So this is exactly what it says. So what we do is, like in this case, a graph convolutional network. So what we tend to do here, we say that like we initialize the nodes. Like we have a H matrix, which is realized like initialized with all the random weights for each of the node. And now what happens when we are doing graph convolutional network? So we are actually picking up a node and taking all the neighbors of them. Now all the neighbors of them to identify the vector H. Like basically the update to the H happens based on a sigmoid. Sigmoid is this like just a nonlinear function. So what does this whole function says? It says that I pick up a node, pull out all the neighbors. So the neighbors are all the J's which are there. And then from I take up their representation. W is just a parameter metric, like it's another metric. Just that's what our model is. So we say that okay, take up all the neighbors, take up their representation, do a linear combination, which is governed by W, like a linear combination, and then weigh them based on the degrees. Like for example, there is a node, a friend of, like let's assume Twitter. So like consider Obama, which has millions of users. So now people just generally follow Obama. Does not mean that they are similar to Obama or they are friend to Obama. So we need to have some sort of like normalization. So that DII is like kind of a degree of the both the nodes. So if you are either a big influencer who generally people follow, or you are somebody who is just following like millions of people, so such nodes need to be normalized. Otherwise, they will just overwhelm the similarity metric, right? So that's the basic thing that's happening up here. And then how do we combine? We combine them by, again, if you think about this second equation, if you think is the left part, which is same as the above part. So what we're saying is that at each iteration, I figured out what is my update should be there. And then I update it back to my own previous representation. Normalized by my degree, like, so that's what it's happening. Now, how do we fit in a graph here? So it's basically you create pairs of all the edges. Like for example, if I'm talking of node say I, then what I do is that either I can pick up all the neighbors, but in case what happens, the graph is like there are some people which have very few neighbors, some people are very high neighbors. Then what we do, we sample the neighbors by a number. Like we can say take only 5 or 10 or like k like some m numbers of neighbors, and then take this pair and push it through the neural network. So that's how we sort of put the structure inside the graph. Now, obviously, the question is that like, okay.
We've got a couple of questions if you'd like to stop and answer. Yeah. So
perfect.
Abdul asked, can the initial solution H be equal to pre-computed high dimensional embeddings?
Yeah, so this is basically, we can obviously do that. The only, there's no, it will actually just sometimes speed up the processing itself. Like for example, if our initial solution H is like when you're taking this high dimensional embedding and they are they are based like they are based on some property of the network, it's sort of telling the neural network that this is a prior information that you can build up. It will indeed help if the embedding quality is good. Yeah, we can do that.
And then we also had another question from Mustafa, who's asked how to ensure adjacency matrix is generalized, not biased towards a node during neural network training while aggregating.
Very good question. I think it's super cool question. Thank you so much. So yeah, so this is a very important consideration when we're training things. And the way we do this is that by sampling the nodes randomly, like we sort of like, we're not just picking up one node, and that's where it's very critical that like we need to ensure that we're not just sampling the edges, but sampling the nodes, because sometimes like if we sample the edges, what may happen is that a few nodes which have high connection with the rest of the network may come prominently, but it also depends sometimes upon the like the network or the problem involved. But yeah, the way we handle this is like by doing a good sampling or good what you call as picking up a good set of nodes or edges.
And we've also had another question: how does second, third, or nth level of node represented in mode model training?
Very good question. I think this is super awesome. So very good question. So what you can do is that, like, usually what we typically do is to do a traversal around it. Like I think I'm like, thank you Raghav for actually making that observation, that while I was just saying that about like sample the neighbors. You can actually pick up neighbors. Like the definition of picking up neighbors is pretty volatile in most of the GNNs. So you can directly pick neighbors like immediate adjacent nodes, or you can actually go ahead and say like, I want to do a 2-level or 3-level nodes. Another option, which is like most of the algorithms, what they do is that this node selection or the neighborhood selection is a separate process. You can actually run a DFS around yourself, or you can do a random walk around yourself. So depending upon how you can generate the data, like how much computational resources you have, you can generate the neighborhood outside. But like as the general mechanism, there is no restriction on having only first level. But you have to do that complexity, like the complexity increases, by the way. Like if you want to go like 3 steps or 4 steps, or maybe say n steps, it's practically doing a n level deep DFS, which needs to be done there. There are more recently, there are more what you call as depending on certain graphs. Like for example, if the graph is like say Facebook graph, so if you talk about like 1 billion user, and then most of the users are connected to say only 100 people, doing a DFS is the most effective way. But if it's a graph is a very it's like heavily dense graph where say the nodes are connected to like say n by 2 nodes or n by k nodes, so like very densely connected, you can do some heuristics like pick up some two random pair of nodes and check out basically the connectivity between them. So it depends upon like the density or the number of edges and number of vertices to figure out what's the optimal way. Should we do a DFS starting at a node, or shall we pick up random pair of nodes and check whether the path exists between them, and then hence push it back to them? So this, like, there are lots and lots of approximations which are available, and like each different research work tries to use some of them depending upon their use cases. But yeah, very good question. Thank you so much for asking it. So yeah, that's one of the things that we did. Sorry. So another option which happens, like if you take up graph convolutional networks, the key problem there is that like we always weigh the edges or the representation based on the weight of the neighbor. That's a key observation. Sometimes the neighbors are not actually good. For example, like a very clear example is like, as we said, like I'm continuously referring to the Twitter example, but like your followers is not a good representation of you. And so what can happen is that sometimes we even want to allow for some more, like we even want to control that which nodes do we want to consume. And this is the standard setting of an attention thing. So attention networks are basically, you can actually look at the other data which is there and specify that where do you want to put more attention to, like which nodes you want to pay more attention, or which nodes, like while you're aggregating them, which particular nodes you want to weigh more. So that's where the attention network come, and this the whole the idea is to control the effect, like the weights may be noisy, and that's what. And this is similar, the motivation is exactly similar to what we do in say text. We say that when we have a word like sun rises in the, and then blank, this blank depends on rises and sun. and not so much on in the kind of thing. So you can, attention provides that mechanism to look at certain pieces of information and give them more weightage. So the same thing can come up here. Cool. So now we move on to, this is one of the problems. So just to recap, we were looking at node node classification or node prediction. And what we were saying that we have node representations. Using the node representations, we want to learn the node representations which capture the structure property of the graph and use this representation to do a classifier. It can be like a simple one-layer neural network classifier to classify the node. Now, the second problem that comes up is on the front of link prediction. So link prediction is a slightly different problem. So while node classification is a individual node problem and you're using the structure, link prediction inherently is a property of two nodes. So a social network can be friend recommendation, whether like A and B are friend to each other. For user and Netflix, it could be a movie recommendation. For a citation network, this could be a co-author prediction, like two authors wrote a paper together or did some work together. Now, conventional methods, if you think about, are like common neighbors kind of thing. Like you can actually say that if two nodes have a lot of common neighbors, or if two nodes, random walk of two nodes, the number of shortest path between two nodes is very high, then you sort of say that there should be a link existing between them. You can also do matrix factorization. So matrix factorization means like the adjacency matrix which is there, you factorize it. So what does it mean? It means that, yeah, I have this huge graph, but then I can represent them with limited information. I can say that there's some Uber way because of which nodes are connected to each other. So in case of say Twitter, you can say that I know that people connect to each other because of interest. So instead of capturing the whole Twitter graph, I can have a simpler representation. Very good question, I think. Can GNNs be used with a graph representation of a program rather than a network of users to tackle problems like code generation analysis? A very good question. Yeah, so I think we can do that as long as, like, for example, there has been recent work where people have actually generated the code. And if you think about like typically what the compilers do, right? They have this DAG analysis, like they take the program and then break it into like a direct cyclic graph where each node is a small piece of code. And so if we can represent our code like that, we can indeed use the same kind of representation. So in this case, if we are using it for say code generation, what we are trying to say is that like we are trying to either predict a node that certain node should happen, or we can look at the whole program as a graph prediction problem. Like we can say that like given up like possible kind of nodes, you can say that how do I like what is a DAG structure that can come out, or what is the way you can lay out the program. The key questions there though is that like the basic ingredients of the code we need to have, like the nodes should be there, like, and we can also, what we can do is that leverage not only graph, but we can leverage say like another text processing to generate individual code snippets, like small pieces, and then connect them together. So we can say like for can be one loop, and you can break the program like you can say that any program, if it's a program for sorting, so it should have a for loop which does the swapping, and then it can an input and output. So you can assume that there is a graph running from input, processing, and output, and so on. So yeah, it can be done. I don't think that we have still made all the like we have still come up with a replacement for all the software engineers. But yeah, like I think there was some people released, I think, using I think DeepMind or one of the things where they have generated code. They have tried to generate code, and it's sort of achieved like 53% or something on code forces. That was one of the news I read recently, where I think OpenAI or DeepMind, one of the two things was used to generate like code, and it exactly did the competitive programming. Like you given up a problem statement, it could figure out a piece of code that can try to replicate that thing. But yeah, so those things are already happening. That's a very good question though. Cool. So I think let's move on to the next part of it, like link predictions. I think the given is exactly the same. We have a graph adjacency matrix and a node attribute matrix. Now what you can do is that like there are two approaches that people have used for link prediction. One is primarily based on node based. So we say that you have learned the representation for nodes, and now you basically aggregate the neighborhood and try to predict whether like the representation should be such that every time where there is an edge between the two nodes, the node should be similar, like in one way or the other. Like you can say, I do a cosine similarity or some measure, and you say that measure should be high if they are linked together. So then the link prediction problem basically becomes like you learn take the whole graph, learn the representation such that for every pairwise thing you have a higher score whenever the edge exists, and every time the edge doesn't exist, the score is low. So just learn a function like that. There are more nuanced approaches which are more subgraph based. So they say that instead of this is like a node based approach is not adequate because you are just looking at two nodes, and sometimes that's just not feasible. And a good example is that like I want to predict an edge in Twitter between me and say say a good example can be like Obama. But then it depends upon my friendship. Like for example, if from my friendship or my other followers you predict that I'm typically interested in political figures, then there are chances that I might be interested in Obama. But just taking Obama's node and my node may be not sufficient. So that's the whole idea behind subgraph base, that you actually pick up the place where you want to extract the link. So between me and Obama, we construct up a small local subgraph and say represent this, and then try to do the prediction. So that's the basic idea behind subgraph thing. Now, I think there's couple of proposals which are made on this kind of front. So one of them I just want to mention here, which is like graph autoencoder kind of thing. So the idea here was that we basically pick up this node representation as we seen in the before, and then what we did was we take this let's assume we have Zi and Z. These are two nodes like I and J, and this is our adjacency matrix. So what we say is that learn a function such that this particular function, which is like sigmoid over representation, so this should be able to predict Aij. Like for example, every time there is an adjacency, like there's a one between like I and J adjacent, this sigmoid should sort of emit out 1, and every time this is 0, this should emit out like 0. So like basically take this multi-dimensional sigmoid and learn it. And the idea here is that this Z is learned as a neural network. Now, when we do this, we want to optimize. Like how do you predict? Like how do you ascertain how good we are matching? So that's where the loss function comes. So what we are doing here is like it's this component basically broken off two things. So this is the actual value into whatever we predicted. Like this is called as cross entropy. So what we're saying is this is what we wanted and this is what we predicted. And similarly, whenever this edge should not exist, we should also not be. Like, so for example, if you think like Aij was high, like 1, and we predicted 0. So then this is like log of 0 is like infinity. So this becomes like log of infinity is 1. So this loss function becomes high. So we want to be closer to what is actually being predicted, like in both in zeros and ones. So, or for example, like if you always predict 1, then this quantity whenever it's 0 will actually give a higher loss. So that's what we are trying to do here. Cool. Now let's just look at, I just want to move towards the closure. So I think at this point of time, we have done a bunch of things. So which is like, we sort of looked at node representation problems. We looked at link representation problem. Now, I think we just want to look at a few of the examples where we can use the graphs. Okay, before we go do there, there's a question by like, are adjacency matrices and node representation matrices related? Doesn't one influence the other? Where in the architecture is that taken into consideration? A very good question. So there are actually three kind of things. Like, so like if you're talking about node representation in terms of the final matrix, which is like the representation of the node that we derive, so that is actually dependent on the adjacency matrix. Like there's a very core representation. So if we look about it, this is precisely what we're trying to do. So in this case, this X that we're using, this A kind of thing, is what we're using is sort of an learned adjacency matrix. Like X is the representation for the node, and A is the actual adjacency. So the adjacency matrix is indeed used to learn the representation matrix, and the core idea is that the node representation has to be such that it sort of explains the structure. So they have like very close, like it's sort of like kind of one-to-one correspondence, but not necessarily always, because sometimes the structure can like a structure can be represented by like a same structure can be explained by multiple node representations. There are infinite such node representations possible, but yeah, they have a very close sort of like a clearly one-to-one kind of like a very close relationship between the two. And wherein the architecture is that taken into consideration is because like when we're actually learning, we learn the X but optimize on A. So that's the connection. So you want to learn that X which optimizes your actual adjacency. So not any choice of representation will be like useful. Cool. So I think, yeah, so now what I want to do is that like towards the last 5 minutes or so, I want to spend some time into looking at the applications. So where do like how can they come? So one of the few like what I've done here is that like I actually pulled out a bunch of papers which are given at the below of this slide, and these papers talk about like how this particular thing was done. So one of the first example which we are sort of looking at. Oh, sorry. Yeah, I think, sorry. Yeah, I think there is a overlap, but the idea there, what I was trying to do, this slide has a bit problem, but yeah, what I was trying to show here is that like one of the way which people did use these things into the research is to actually take the image and then basically assume that image is broken down into patches, and that patches can be treated as a graph. The another approach which I put up here is that like what we have is like initially object segmenter which takes up an image and proposes the augment the various objects which are there, and then what we do is that we use them to finally label the scene graph, where we say that each of the box what it means, what is the relationship with other box. And if you look at this particular proposal in the paper, this talks about like taking up a edge feature, like basically both the node and edge feature, and then combine it through the neural network. This is another example which which I'm talking about from the text part of it. So the first paper which talked about like we have heard about bag of words. So this particular thing, what it did was that instead of creating a bag of word representation, they talked about like a graph representation. So here what happens is that every time these, like say for example, if there are two words who have co-occurred within a window of say 3, 5 or like k words, then we create an edge out of it. So they picked up this particular graph to represent a text corpus instead of like using a bag of word representation and like TF-IDF. They say like it's like TW-IDF, which is like a kind of graph of a word, and then based on that you predict out the various the properties of the text. On the right hand side is similarly thing around like on the right hand side there is a thing around like a knowledge graph. So this knowledge graph is about like travel, in this case about travel, and it's trying to figuring out like what's the relationship between the events and the dates and so on. So there is like just two examples. There are lots and lots of examples in the literature where people have taken up a problem and they have represented as a graph and then applied like say a graph neural network. So the key thing that I want you to take from this particular talk at this point is that like yes, graphs are actually a very rich information source, a very rich formalism, a very rich way to represent our actual problems, number one. Number two, there are two kinds of problems that we can pose in graph. One is on the front of node recognition, and on the second on the front of link prediction. Number three is that like whatever you do, link or node prediction, the key idea in the neural network is to come up a representation for a node or a link in such a way that your actual problem can be represented as a vector over these representations. So if it's a link prediction, the two vectors should be closer. If it's a node prediction, then the representation of the vector should be such that you can build a classifier and so on. And finally, because you have this functionality of GNN, then a lot of problems can actually pose into graph and then solve through GNN, which allows us to capture a rich structure of the underlying problem to address the problem there. Yeah. So with that, yeah, I think I bring my talk to an end, and any questions I'm like happy to answer.
We have had a question asking, can graphs be used for the explainability of AI?
Yes, a very good question. So yes, so there are like very okay. So I think we can use the graphs to do the explainability of an AI, and I think that depends. The answer, like the explainability that we can impart, depends upon how we are, like what kind of problem we are actually training for. So if suppose we are directly using a causal graph and learn it, we can obviously figure out we can look at the nodes, figure out the kind of representation, and then do some basic visualization to say that when a decision is being made, what would have been the decision. So that's one of the way to do that. Number two, if suppose your actual graph, your actual prediction is not involving graph, then what we can do is that we can assume that whatever node, whatever representation of the original problem is there, we can again take the vectors and try to construct a graph out of it and do a reasoning on top of it. So there are like two ways to do that, and there are more which are reported in the literature. Okay, can graph neural network used for reinforcement learning? Yes, there are extensions to GNNs in terms of reinforcement learning. A critical part to note in reinforcement learning is that how do we basically do a credit assignment? Like if you're doing multi-stage kind of problem, like for example, any kind of like a strategy that we're planning. So how do we do the credit assignment? Now, in my understanding, the graph representation, like these are sort of orthogonal kind of thing that we have. If we can represent the whole problem, like let's say you are taking multi-step paths in the graph, and then using that graph to learn through GNN can directly answer the graph. Sometimes you can use multiple GNNs or multi-stage GNNs to impart like credit assignment. So the problem of reinforcement learning can actually be solved either through a single graph neural network, provided you have multi-layered stuff, or multiple graph neural networks for each of the stage of the decision making.
Thanks, Rahul. We've also had another question asking, can graph networks be used for fraud analytics?
Yes, we can. I think it's a very good question, and it's one of the very good interesting application that people have. Like it's not very well explored as yet, but because I think it becomes a bit complex in the sense that like the compute power, the computational resources for the graph neural is sort of a bit more on the higher side. But yes, it's a very interesting thing. And just to give a very good sense, right? Let's assume we want to figure out a fraudulent login. Now, there are a couple of things which is there. Number one is that the data is very limited. There are only few fraudulent logins that can happen. So that immediately implies that you need to capture a lot of good semantic structure, like a lot of domain knowledge that you want to capture. And a graph-based system can actually help you do that, because we can express that login process itself as a relational thing. We can say that you have to be like, in the past, you have been always logging from say London, and your typically browser is this, and blah is this, and a lot of such characteristics, a lot of sequential characteristics which are there, and we can represent them through rich graph structures. And once we do that, we can say that I will learn a graph for not for a fraudulent user, but for a genuine user. So basically to understand the graph of a genuine login, and then use fraudulent as an anomaly. So this is sort of much easier to model than just like taking a linear kind of model where we actually take up a lot of features, like how many times you have logged in, what cumulative numbers and so on, where we completely destroy the relational aspect of it. And so yes, in fraud, I have seen a couple of papers which claim that they have like shown a lot of good performance. So I can actually share the references there. But yeah, it is one of the area where this graph neural networks are being used, and it's prominently used. That's a very good question, by the way.
I think that concludes. Oh no, we've had another one. I've read that neural networks are not generally ensembled, due to being computationally expensive. Is this correct? And as power increases, will this change?
Again, a good question. So I think there are two aspects to being creation of ensembles. So I think if you think about neural networks, right, like neural networks in itself is an ensemble, like when you're actually putting a lot of them. So if you think about say a conventional SVMs or linear regression, logistic regression, we can think about a neural network as already as an ensemble. Now, if you think about saying that, okay, I have a multi-layered deep neural network, which is like super expensive to predict and so on, and I want to create more ensembles out of it. Yes, the compute power is only restriction there, and but that will be like true even for other methods also. Like if I take a random forest, which like say 10,000 trees and so on, and you create like 2 random forests or 3 random forests, the compute itself becomes complex there as well. So compute is one aspect of it. The second aspect of is that like usually the second aspect of it, like looking at like say neural network like ResNet. ResNet is one of the neural network that we use, has like I think close to 100 plus layers. So for all technical definition, it's sort of an ensemble. It's a sequential ensemble. You can think of it as a gradient boosted decision tree. So it's not a decision tree, but like it's sort of an ensemble of things. So it's already ensemble. But that's one way of looking at it.
Okay, I think that is all for the questions. I'll just give anyone a minute in case they've got anything additional they want to ask.
No, I think, yeah, that's from my side.
I think we've got the questions. Massive thanks, Rahul, for obviously putting together this session and sharing your knowledge. For everyone watching, a recording of this webinar will be uploaded to the Amicus Recruitment YouTube page, and from there you can also find other series that we've recorded from our live series. So don't forget to like and subscribe to that page to make sure you find out when we post new events. If there's any follow-up questions from this, or you'd like to reach out to Rahul or myself, then please feel free to do so. Connect with us on LinkedIn. And yeah, any follow-up questions, let me know. Can we have more sessions from Rahul? I'm sure we can.
Yeah, my pleasure. I love the audience. Like the questions were so thought-provoking, and yeah, I think I love this audience. I would desperately want to come back again in this kind of session.
Yeah, it's been a great interactive session. We've had a lot of good questions, a lot of knowledge shared. So we'll definitely be back with another episode.
Thank you.
All right. We'll leave it there. But thanks everyone for joining, and have a great evening. Thanks.